Okay, ready? Okay, so let's continue with some more non-stationary time series analysis tools. Again, let's have a quick review. We want to do some signal processing. Okay, give you a signal that is composed of 3 components, and these 3 components have some nice properties: amplitude modulation and instantaneous frequency. And the ultimate goal is to find something called ideal time frequency analysis or representation, which is a function defined on 2-dimensional space, time and the frequency. And you hope that in the time frequency representation, the pattern of the measure captures all the desired information like frequency, amplitude, and so on, so that you can achieve any kind of time frequency, any kind of signal processing missions you have in mind. And so far we have discussed several time frequency analysis tools: short-time Fourier transform, synchro squeezing, up to Wigner-Veal distribution or ambiguity function. But that is not the end of the story. Actually, there are so many different ways we can modify Wigner-Veal distribution, ambiguity function, and so on. And that's called Cohen's class. And there is another type of modification called affine class, which is associated, can be viewed as different types, geometric types in the time frequency domain compared with Cohen's class. But we will not go to affine class. If you are interested, you can go to the textbooks. We will focus on Cohen's class today, and maybe in this whole lecture. So Cohen's class. You may remember in the in the Wigner-Veal distribution, the limitation of Wigner-Veal distribution is the interference of different components. Or even if you have one component, okay, if the frequency changes, then there will be some interference. And we want to find a way to cancel the interference. And I have shown you an idea of the cancellation, like spectral. And how to do it. That is, you see that, the Mollet pattern, the interference actually has a high frequency oscillation. So maybe we can apply some kind of low pass filter to cancel the high frequency oscillation so that we can get the desired time frequency representation. Yes, that is the idea. And the idea is actually the Wigner-Veal distribution. You apply some kind of kernel. And depending on the kernel, you have different names. But as long as you apply kernel in this way, this is called Cohen class. Okay. For example, the spectrogram is the magnitude square of short-time Fourier transform. So you can view it as a quadratic type time frequency analysis because you take square. Okay, and this guy, spectrogram, comes from what? It comes from choosing the kernel as the Wigner-Veal distribution of the kernel, and when you run this integration, it is actually a convolution type. So you can say spectrogram is actually a Cohen class, and it has some nice properties. How about the other possibilities? Well, there are a lot actually. Suppose you consider the Cohen class of the convolution type, not anything too crazy, it's a convolution type. And suppose you take the kernel to be just a delta major, that is equivalent to do nothing. Okay, then it is just Wigner-Veal distribution. How about if now we consider in time we don't do anything, time is a delta major, but in the frequency domain, you have some kind of Wigner-Veal distribution. Then that is called pseudo-Wigner-Veal distribution. That is, you only smoothen on the frequency axis, but not in the time axis. Then that's called the pseudo-Wigner-Veal distribution. That is equivalent to do the following. You have the window H star and F star but you multiply it by some window in time domain. Okay, so that is pseudo-Wigner-Weyl distribution, and that is the result. If you only smoothen the frequency axis in this example, you see that well, this is a Wigner-Weyl distribution, right? There's a lot of interference. After smoothing the frequency axis, well, you get some cancellation, right? The frequency axis blurring is somehow eliminated, but in the time axis, it is not eliminated. You can still see some pattern. So why? Because the oscillation pattern is not only in the frequency axis, but also in the time axis. And in pseudo-Wigner-Weyl distribution, you do not cancel the time axis. So you can also consider smoothing the frequency axis. Okay, so there will be some kind of another example. For example, if you have delta major, two delta major, and as you remember, in the frequency, in the Wigner-Weyl distribution, you have two components and an interference in time domain. And in pseudo-Wigner-Weyl distribution, it will very well cancel the interference, because interference is oscillatory in the frequency axis. So you cancel it. Okay, because the oscillatory direction is cancelled by the smoothing direction. How about if we consider more? Let's consider a smoothed pseudo-Wigner-Weyl distribution. That is, you will have time domain and the frequency domain, both. You smooth both. And this will be the result. You smooth both the frequency axis and the time axis. Then what you see is, hey, the interference in between is now fully cancelled. So that you get something more informative. And you can consider the delta major again as before. You see, in the Wigner-Weyl distribution, you have two lines and the interference. And this time, we have interference cancelled in the frequency axis, so it is gone. But you also apply the smoothing in the time axis, so that you see it is blurred. And if you pay attention, you will see that on the right-hand side, this smooth pseudo-Wigner-Weyl distribution is actually very similar to short-time Fourier transform. It's very similar to short-time Fourier transform. Because in short-time Fourier transform, you also do the smoothing in both time domain and frequency domain. But the window, the filter, is chosen by the Wigner-Weyl distribution of the Gaussian, of the window you choose for short-time Fourier transform. But here, in smooth pseudo-Wigner-Weyl, the time domain and the frequency domain filtration in the Wigner-Weyl distribution are chosen by you separately. So you can consider more examples. There are actually several variations. For example, when K is 1, it's called pseudo-Wigner-Weyl distribution. When K is delta, you get the spectrogram, and so on. So there are many variations. Well, it's impossible to tell you to summarize everything, but in the textbook there is a huge table you can find, and it contains almost everything. And we can also consider Cohen class based on ambiguity function. You remember what ambiguity function is, right? Ambiguity function is nothing but Fourier transform of the Wigner-Weyl distribution. Okay, and it has some basic properties of the interference and the auto turn, and the crossover. They are related in this way. So you can also consider, well, not the Wigner-Weyl distribution smoothing, but in the frequency domain, you have ambiguity function, you multiply by some window, and you run Fourier transform. Okay, that will be another set of Cohen classes you can consider. So So for example, if you consider this phi to be of this form, Gaussian form, this is called the Choi-William distribution. Okay, it will suppress the interference away from the origin except for the cross term located on the eta and tau axis. That's several properties. And then if you consider just the interference in this format, tau, eta times tau, this is called the Rorschach-Zec distribution. Okay, so there are several variations. That's the only thing I want to tell you a lot. And this is the example for this example. Again, you have a lot of interference. Okay, and if you run the Choi-William distribution, that is what you get on the right hand side, which is actually quite nice, quite concentrated, and you get all the information recovered. And this is ambiguity function. Okay, and you can also compare the Wiener-View distribution and the Choi-William distribution. If you have two components, x1 and x2, and you can see there's an interference as I showed you before. And if you run the Choi-William distribution, you get two components recovered quite nicely. Okay, and we will have more real examples in a bit, but we have real example next. But this is the example you can see. First, this is an EEG signal. Okay, spectrogram will give you something quite nice in the middle. And this is a Wiener-View distribution. You can see a pattern and a lot of strange patterns. And this is a Choi-William distribution, which is actually quite nice. Okay, and you can find all the codes and the resources again in Patrick Flandrin's and the website, and that is a time frequency toolbox prepared by Patrick Flandrin and his team. And there will be textbooks that contain or include almost all the information, and there's even a big table contains a lot of different variations of Cohen classes or affine classes, which I will not explore. Thank you.